History of light-emitting diodes. For the vast majority of human history, the artificial generation of light was inextricably bound to the generation of heat. From the earliest controlled fires, oil lamps, and tallow candles, to the sophisticated enclosed tungsten filaments perfected by inventors like Thomas Edison and Joseph Swan in the 19th century, illumination relied on the physical process of incandescence. Incandescence is a thermodynamic mechanism wherein an electrical current or chemical combustion heats a material to extreme temperatures until it begins to glow, radiating electromagnetic energy across a broad spectrum. This mechanism, while world-changing and foundational to modern civilization, is fundamentally inefficient. The vast majority of the applied energy is lost to the environment as invisible infrared thermal radiation, heat, rather than being emitted as useful visible light. The paradigm shift from thermal incandescence to quantum mechanical luminescence marks one of the most profound and impactful technological evolutions of the 20th century. The light-emitting diode operates on an entirely different scientific principle known as electroluminescence. Electroluminescence is a phenomenon in which a solid material emits light directly in response to the passage of an electric current without the need to first generate thermal energy. Unlike incandescent bulbs, which operate in the macroscopic, brute force realm of thermodynamics, the light-emitting diode is a solid-state electronic device governed entirely by the microscopic and highly precise laws of quantum mechanics. The transition from the initial accidental laboratory observation of a curious dim glow in a mineral crystal to the mass production of highly efficient semiconductor light sources was not a sudden breakthrough. Instead, it was a methodical, decades-long evolution that required mastering the intricate physics of crystalline structures, inventing novel techniques for chemical vapor and liquid phase epitaxy, and overcoming severe thermal, optical, and material engineering constraints. Before the advent of the high-brightness blue light-emitting diode in the 1990s, which ultimately unlocked the capability for general white light illumination and won the Nobel Prize in Physics, early diodes were restricted primarily to low-power indicator roles, numerical readouts, and alphanumeric displays. However, this formative pre-blue era laid the inescapable and vital groundwork for the modern optoelectronics industry. Through the rigorous exploration of binary and ternary semiconductor alloys, such as gallium arsenide phosphide and aluminum gallium arsenide, scientists engineered the atomic band gaps of materials to conquer the infrared, red, orange, yellow, and green regions of the electromagnetic spectrum. This comprehensive historical analysis details the theoretical origins, the first practical inventions, the material science breakthroughs, and the early commercial applications of light-emitting diodes prior to the blue light revolution. The quantum mechanics of solid-state electroluminescence. To fully appreciate the historical milestones of early semiconductor light emission and the formidable challenges faced by early inventors, it is first necessary to examine the fundamental solid-state physics that governs the phenomenon for a general audience. Electroluminescence in a solid-state diode occurs at a microscopic boundary known as a p-n junction. A semiconductor is a material whose ability to conduct electricity falls between that of a conductor, like copper, and an insulator, like glass. Through a process called doping, scientists introduce specific chemical impurities into the semiconductor crystal lattice to alter its electrical properties. When a semiconductor is doped with an element that has extra valence electrons, it becomes an N-type material, teeming with negatively charged free electrons that can move about the crystal. Conversely, when the semiconductor is doped with an element that has fewer valence electrons, it becomes a P-type material. The missing electrons in the P-type material create voids in the atomic structure known as holes. In the realm of quantum physics, These holes act as positively charged particles that can move freely through the crystal lattice, just like electrons. When an N-type material and a P-type material are joined together, they form a p-N junction. If a forward bias electrical voltage is applied across this junction, the electrical pressure forces the negatively charged electrons from the N side and the positively charged holes from the P side to migrate toward the central boundary. As these charge carriers meet within the central depletion region, they undergo a process known as recombination. During recombination, an electron drops from a higher energy state in the atomic structure, known as the conduction band, down to a lower energy state, known as the valence band, to fill one of the empty holes. According to the fundamental laws of physics, specifically the conservation of energy, the energy difference between these two states cannot simply disappear. This energy gap, known as the band gap, dictates how the energy is released. In a direct band gap semiconductor, the momentum of the electron and the hole are naturally aligned. This allows the excess energy to be released purely and efficiently as a single photon of light. The wavelength, and thus the perceived color of the emitted photon, is inversely proportional to the energy of the band gap, a relationship defined by the Planck-Einstein equation. A smaller band gap releases lower energy photons, which correspond to invisible infrared or visible red light, while a larger band gap releases higher energy photons, producing colors like green, blue, or ultraviolet. Conversely, in an indirect band gap semiconductor, the minimum energy of the conduction band and the maximum energy of the valence band do not align perfectly in terms of atomic momentum. For an electron to recombine with a hole in such a material, the momentum difference must be resolved. This requires the involvement of a quantum of lattice vibration, known as a phonon, which must be either absorbed or emitted during the recombination event. Because this is a complex three-body interaction involving an electron, a hole, and a phonon, the probability of radiative recombination, producing light, is drastically reduced. Instead, the vast majority of the energy is dissipated non-radiatively as heat. This fundamental physical distinction between direct and indirect band gaps would go on to define the commercial successes and agonizing failures of early semiconductor materials throughout the 20th century. The era of early electroluminescence. The earliest recorded observation of artificial electroluminescence in a solid-state material occurred almost by accident in the first decade of the 20th century. In 1907, British engineer Captain Henry Joseph Round was conducting experiments at the Marconi Labs in Chelmsford, Essex. Round was a highly accomplished inventor and a personal assistant to the famous radio pioneer Marconi. Round, who would eventually amass 117 patents over his lifetime and make vital contributions to vacuum tube development and radio direction finding, was investigating the asymmetrical electrical conduction properties of early radio components. Specifically, Round was experimenting with a cat's whisker detector, which was an early, primitive type of point-contact semiconductor diode used to detect and demodulate radio frequency signals. During his investigation, Round applied an electrical potential difference across a crystal of carborundum, which is the commercial name for the chemical compound silicon carbide. Silicon carbide is a hard crystalline material that occurs naturally in very small quantities, but was largely synthesized for industrial abrasives. When Round applied a relatively low voltage of 10 volts between 2 points on the crystal sample, he observed a curious, unexpected phenomenon. The crystal emitted a dim, yellowish light. Intrigued by this cold glow, he increased the applied voltage up to 110 volts and found that a much larger number of crystal specimens began to exhibit the luminescence. He noted that the emitted light varied in color depending on the specific crystal sample and the applied voltage, producing a glow that appeared yellow, green, orange, or even as blue-green sparks concentrated at the edges of the material. Round immediately recognized the novelty of his observation and published a brief 2-paragraph note detailing his findings in the journal Electrical World in 1907. This publication provided the global scientific community with the first official report of light emission directly caused by the application of an electrical power in a solid-state material. However, at the time of Round's discovery, the theoretical frameworks of quantum mechanics and semiconductor energy band theory had not yet been established. Furthermore, silicon carbide is an indirect bandgap material, meaning its light emission was incredibly inefficient and required high, impractical voltages to produce a barely visible glow. Devoid of a practical commercial application and lacking the theoretical tools necessary to explain the microscopic mechanisms of the phenomenon, Round's observation remained an unexploited laboratory curiosity. The scientific world largely ignored the glowing crystal, and Round himself eventually moved on to make significant contributions to the development of thermionic vacuum tubes and early radio transmitters. The phenomenon of solid-state light emission lay largely dormant and ignored by the broader scientific establishment until the 1920s, when it was independently rediscovered and rigorously investigated by Oleg Vladimirovich Losev. Losev remains a brilliant but ultimately tragic figure in the history of solid-state physics. Born in May 1903 in Tver, Russia, to a noble family with a father who served as a retired captain in the Tsarist Imperial Army, Losev faced severe socio-political barriers following the Bolshevik Revolution and the subsequent Russian Civil War. Because of his upper-class aristocratic background, he was systematically denied access to formal higher education and high-level academic research positions. Despite completely lacking a university degree or formal academic credentials, Losev possessed an innate engineering genius. He secured a low-level position as a technician at the Nizhny Novgorod Radio Laboratory, where he was tasked with testing components for Soviet radio sets. It was here that he began extensive pioneering experimental work on semiconductor crystals. While researching biased crystal junctions in 1924, Losev independently observed a greenish spot of light emanating from a silicon carbide point contact diode when a direct current was passed through it. Unlike H.J. Round, who merely reported the effect as a curiosity and moved on, Losev dedicated years of intense focus to understanding the underlying physics of the glowing crystal. Losev's experimental methodology was remarkably advanced and exhaustive for his era. To determine whether the light was simply a result of thermal incandescence, the crystal heating up until it glowed, or an entirely new physical phenomenon, he devised a clever experiment. He measured the evaporation rate of the chemical compounds from the surface of the crystal during operation. Discovering no significant thermal evaporation or extreme localized heat, he correctly concluded that the luminescence was a genuine form of cold light. He proceeded to map the current voltage characteristics of the diodes with incredible precision, establishing the exact current thresholds necessary to stimulate the light emission. He also studied the device's behavior at extremely low temperatures by submerging the operating crystals in liquefied air, a predominantly nitrogen-based mixture, to prove that the light was non-thermal in origin. He even demonstrated that the light emission could be modulated rapidly by applying an alternating current up to frequencies of 78.5 kHz, proving the device's potential for rapid switching. Losev published his findings in a landmark paper in 1927 in the Russian journal Telegrafia и Telefonia bez Provodov, Wireless Telegraphy and Telephony, titled Luminous Carborundum Detector and Detection with Crystals. This document provided the first comprehensive scientific study of the light-emitting diode, quantifying the spectral emission and the required electrical polarities. Furthermore, Losev possessed a profound intuitive grasp of the underlying physics that was decades ahead of his time. He hypothesized that the cold light emission was governed by the emerging principles of quantum mechanics. Specifically, he theorized that the phenomenon was the exact inverse of Albert Einstein's famous photoelectric effect. While the photoelectric effect described light photons striking a material and knocking electrons loose to create a current, Losev correctly deduced that his crystal was taking an electrical current and converting it directly into light photons. He even wrote directly to Albert Einstein detailing his theories, though the correspondence unfortunately went unanswered. Losev immediately foresaw the practical commercial applications for his discovery. He successfully patented a device he called a light relay and explicitly predicted the future use of semiconductor light sources in high-speed optical telecommunications. His solid-state inventions extended far beyond optoelectronics. He also explored negative resistance in zincite crystals, building the first solid-state amplifiers, electronic oscillators, and superheterodyne radio receivers 25 years before the invention of the transistor at Bell Labs. His amplification technology was dubbed the Christodyne principle by publisher Hugo Gernsback. Tragically, because his pioneering work was published primarily in Soviet journals during a period of intense geopolitical isolation, and because the prevailing scientific consensus of the era was heavily focused on the rapid advancement of vacuum tube technology, his monumental achievements were largely overlooked by the global scientific community. Losev received no significant recognition or financial reward for his discoveries during his lifetime. He perished from starvation at the age of 31 on January 22, 1942, during the brutal siege of Leningrad in World War II. He left behind a legacy of 43 publications and 16 author's certificates, Soviet patents, that effectively chronicled the true, theoretical, and practical birth of the light-emitting diode. The first practical inventions. Following the end of World War II, the landscape of physics was irreversibly altered by the invention of the bipolar junction transistor at Bell Telephone Laboratories in 1947. As scientists rapidly deepened their understanding of semiconductor doping, the behavior of PN junctions, and the mathematical modeling of band gap engineering, the necessary theoretical and material foundations for modern light-emitting diodes finally began to solidify. By the mid-1950s, the research focus shifted away from erratic, naturally occurring indirect band gap crystals like silicon carbide. Instead, researchers turned their attention to precisely engineered binary compounds forged from elements found in group 3 and 5 of the periodic table, such as gallium, arsenic, phosphorus, and indium. In 1955, scientist Reuben Brownstein, working at the Radio Corporation of America, RCA, made a critical observation. He reported the emission of infrared light from simple, artificially constructed diode structures composed of gallium arsenide, gallium antimonide, and indium phosphide while operating at room temperature. Because gallium arsenide features a direct band gap of approximately 1.4 electron volts, it inherently facilitates highly efficient electron-hole recombination, bypassing the momentum conservation issues that plagued silicon carbide. However, the 1.4 electron-volt energy level directly corresponds to a wavelength in the near-infrared region of the electromagnetic spectrum, rendering the emission completely invisible to the unassisted human eye. Building upon Brownstein's foundational work, researchers James R. Beard and Gary Pittman at Texas Instruments made a major commercial breakthrough in the fall of 1961. While testing a gallium arsenide tunnel diode built on a semi-insulating substrate, they discovered that the device emitted significant and highly efficient infrared radiation when forward biased. Realizing the commercial potential for optical data transmission and sensing, they immediately secured a patent for the infrared light-emitting diode. Following this, Texas Instruments subsequently released the SNX100 in 1962, marking the world's first commercially available infrared LED product. While these infrared devices were crucial for the development of early remote controls, automated card readers, and optical sensors, the ultimate quest for a visible solid-state light source remained frustratingly unfulfilled. The historical breakthrough that successfully brought semiconductor light out of the infrared shadows and into the visible spectrum was achieved by Nick Hulenyak Jr. in the autumn of 1962. Hulenyak, a son of immigrants from what is now Ukraine, was a brilliant electrical engineer who had the distinction of being the first graduate student of John Bardeen, the two-time Nobel Prize laureate and co-inventor of the transistor at the University of Illinois. After brief stints at Bell Telephone Laboratories and the military, Holonyak joined the General Electric Advanced Semiconductor Laboratory in Syracuse, New York. At General Electric, Holonyak found himself competing in a fierce global race alongside massive, well-funded research teams from IBM, MIT, and RCA to develop the world's first semiconductor laser. His immediate colleague at the General Electric Schenectady Laboratory, Robert N. Hall, successfully developed a functional semiconductor laser using an off-the-shelf gallium arsenide crystal. However, just like the earlier diodes, Hall's laser emission remained firmly trapped in the invisible infrared spectrum. Holonyak, driven by a profound desire to visually observe the lasing phenomenon rather than relying on infrared optical sensors, resolved to engineer a brand new device that emitted visible light. To achieve this, Holonyak utilized a masterful understanding of crystal alloy engineering. He deduced that to shift the emission from the lower energy infrared spectrum to the higher energy visible spectrum, he needed to physically widen the energy band gap of the semiconductor crystal. He theorized that by taking a gallium arsenide crystal and substituting a portion of the larger, heavier arsenic atoms in the crystal lattice with smaller, lighter phosphorus atoms, the resulting ternary, three-element alloy, gallium arsenide phosphide, GaAsP, would undergo a slight structural contraction. This atomic contraction would effectively increase the band gap energy, shifting the emission out of the infrared and into the shorter wavelength visible red region of the spectrum. Crucially, Holonyak calculated that if the ratio of phosphorus to arsenic was kept carefully balanced, the material would maintain the direct gap properties necessary for highly efficient light emission. Creating this entirely new alloy from scratch was a monumental metallurgical and chemical challenge. Many of Holonyak's contemporary peers were highly skeptical of his approach, predicting that attempting to mix a ternary alloy would result in a lumpy, inhomogeneous crystal structure that would be entirely unsuitable for creating the delicate p-n junctions required for electroluminescence. Refusing to be deterred, Holonyak designed a customized chemical vapor transport system to build his crystals atom by atom. He placed solid precursor crystals of gallium arsenide and gallium phosphide in one end of a sealed quartz tube alongside reactive chlorine gas. He then subjected the sealed tube to a strict continuous thermal gradient in a furnace. The source end of the tube was heated to a blistering 1,000 to 1,100 degrees Celsius, while the opposite end was maintained at a cooler 850 to 950 degrees Celsius. At the hot end, the volatile arsenic and phosphorus atoms evaporated, while the chlorine gas chemically attacked the non-volatile gallium, transporting it as a gas down the temperature gradient. At the cooler end of the tube, the gallium, arsenic, and phosphorus atoms deposited simultaneously onto the walls, growing perfectly uniform single crystal layers of gallium arsenide phosphide, entirely avoiding the predicted inhomogeneity. To form the critical p-n junction, Holonyak dynamically substituted the chlorine carrier gas with dopant compounds like zinc chloride or tin chloride during the growth process, allowing him to stack N-type and P-type layers sequentially. On October 9, 1962, Holonyak applied an electrical current to his newly forged gallium arsenide phosphide alloy and successfully demonstrated the first practical visible spectrum light-emitting diode. The device emitted a distinct bright red glow. His astounded colleagues at General Electric affectionately dubbed the component the Magic One because its light could actually be seen by the human eye. Recognizing the profound societal implications of his invention, Holonyak confidently predicted in a February 1963 issue of Reader's Digest that his new solid-state lamps would eventually replace the fragile, inefficient incandescent light bulb invented by Thomas Edison, a prophecy that would take exactly 50 years to fully materialize. Material science evolution through the 1970s and 1980s. Holonyak's invention of gallium arsenide phosphide established what came to be known as the alloy road, a systematic, highly intentional paradigm in which the emission wavelength of a semiconductor device could be finely tuned by altering the stoichiometric ratio of its constituent atomic elements. As the technology transitioned from the pioneering days of the 1960s into the rapid commercial expansion of the 1970s, the global scientific community intensely focused on expanding the available color palette and dramatically enhancing the luminous efficacy of these devices. However, engineers quickly encountered a massive roadblock. One major physical limitation of early gallium arsenide phosphide devices was that as researchers increased the phosphorus concentration to shift the emitted color from a deep ruby red to lighter, more appealing shades like orange or yellow, the crystal structure underwent a fundamental shift. The addition of too much phosphorus caused the material to transition from a direct band gap to an indirect band gap. Just like the early silicon carbide experiments, this shift meant that the material suddenly required phonon interactions to conserve momentum during electron-hole recombination, precipitating a severe and catastrophic drop in light emission efficiency. This seemingly insurmountable hurdle was brilliantly overcome in 1972 by M. George Crawford, a former graduate student of Nick Holonyak, who had taken a leadership role at the Monsanto Chemical Company's Electronic Special Products division. Crawford's dedicated research group discovered that the dramatic loss in radiative efficiency could be effectively mitigated through the highly controlled introduction of nitrogen doping during the crystal growth process. Nitrogen, being an element in group 5 of the periodic table, alongside phosphorus and arsenic, acted as an isoelectronic dopant. When incorporated into the crystal lattice, the nitrogen atoms did not alter the overall electrical charge carrier balance. They did not add extra electrons or holes. Instead, because the nitrogen atoms were significantly smaller and more electronegative than the phosphorus atoms they replaced, they created highly localized microscopic energy states within the crystal known as isoelectronic traps. These isoelectronic traps functioned as highly efficient radiative recombination centers. They effectively captured migrating electrons, holding them stationary long enough to facilitate momentum conservation without the need for thermal phonons, allowing the indirect bandgap material to behave as if it were a direct bandgap material. By heavily doping the high-phosphorus gallium arsenide phosphide with nitrogen gas, Crawford successfully invented the world's first yellow light-emitting diode in 1972. Furthermore, the application of this same nitrogen doping technique to the existing red and red-orange diodes resulted in an extraordinary order-of-magnitude increase in brightness. This vital breakthrough massively expanded the commercial viability of the technology, moving it beyond simple dim laboratory indicators and ushering in an era of high-visibility consumer applications. In parallel with the rapid advancements in ternary alloys, substantial scientific research was directed toward pure gallium phosphide, a binary compound with a significantly wider, albeit indirect, band gap of approximately 2.26 electron volts. A major advantage of gallium phosphide was its optical clarity. Because pure gallium phosphide is naturally transparent to longer wavelengths of light, like yellow and red, it proved to be an exceptionally excellent substrate material. It was vastly superior to the opaque gallium arsenide substrates used previously because building a light-emitting layer on top of a transparent substrate allowed far more generated photons to escape the crystal package rather than being uselessly reabsorbed internally by dark substrate material beneath it. Through careful, targeted doping strategies, pure gallium phosphide was engineered to emit a variety of colors. Doping the crystal with complex zinc oxide molecules created deep energy levels within the band gap that facilitated the emission of red light at a wavelength of 700 nanometers. While these pure gallium phosphide red diodes exhibited exceptionally high quantum efficiency, producing 1 to 2 lumens per watt at very low driving currents of just a few milliamps, they possessed a fatal flaw for commercial displays. Their optical efficiency collapsed rapidly at the higher peak currents required for multiplexed digital displays, limiting their commercial dominance primarily to continuous duty status indicators. Alternatively, by utilizing Crawford's technique of doping the gallium phosphide with nitrogen isoelectronic traps, researchers enabled the mass production of the first commercially viable pale green and yellow-green diodes, emitting at 555 and 565 nanometers respectively. Though the overall luminous efficacy of these green devices remained relatively low, often generating under 1 lumen per watt, the human eye's evolutionary peak sensitivity to the green-yellow spectrum meant these devices appeared brilliantly bright for consumer applications, further cementing the technology's presence in everyday electronics. As the industry moved into the early 1980s, it witnessed the next massive paradigm-shifting leap in luminous efficacy with the introduction of aluminum gallium arsenide devices. Unlike all previous devices, which used a simple HOMO junction, a PN junction made from a single type of continuous semiconductor material, the new aluminum gallium arsenide devices relied on complex heterostructures. A heterostructure device is created by layering entirely different semiconductor materials, each with differing band gap energies, precisely on top of one another. By sandwiching a very narrow bandgap active layer between 2 wide bandgap confinement layers, scientists could strictly confine both the injected electrical charge carriers, electrons and holes, and the generated optical photons to a microscopic, highly concentrated central region. This forced proximity vastly increased the probability of radiative recombination, minimizing wasted current. Aluminum gallium arsenide devices required highly precise, modern epitaxial growth techniques to maintain their structural integrity across the different material layers. When perfected, these advanced heterostructure diodes completely shattered previous performance records, achieving astonishing luminous efficacies of 2 to 10 lumens per watt, depending on the specific internal architecture. For the first time in history, a solid-state light source generated a specific wavelength of red light more efficiently than an incandescent bulb that had been filtered through a red plastic lens. This monumental achievement allowed the technology to break out of consumer electronics and directly compete with traditional lighting in demanding, high-flux outdoor applications, leading to the rapid adoption of LEDs for automotive taillights, vehicle brake lights, traffic signals, and massive outdoor moving message panels. Epitaxial innovations, the shift from liquid to vapor phase. The rapid commercialization, widespread adoption, and transition to complex heterostructure designs necessitated radical advancements in epitaxial crystal growth technology. Epitaxy is the highly controlled process of depositing a crystalline overlayer onto a crystalline substrate, ensuring the new layer perfectly mimics the atomic structure of the base. Throughout the 1960s and 1970s, the overwhelmingly dominant manufacturing technique utilized across the industry was liquid phase epitaxy. In the liquid phase epitaxy process, a highly polished substrate wafer was brought into direct physical contact with a supersaturated molten metallic solution containing the desired semiconductor elements, such as molten gallium mixed with arsenic. The entire apparatus was then slowly cooled, forcing the elements to precipitate out of the liquid and crystallize onto the substrate. Because the crystal growth occurred in near thermodynamic equilibrium, liquid phase epitaxy produced crystal layers of exceptional structural perfection and exact stoichiometry. This near-perfect crystalline quality was absolutely vital for early devices, which were highly sensitive to microscopic structural defects that would otherwise kill light emission. However, liquid phase epitaxy suffered from severe, crippling limitations regarding industrial scalability. The physical process was inherently slow, exceedingly difficult to automate for continuous production, and struggled immensely to uniformly coat large area wafers. More importantly, as device designs evolved to require the ultra-thin, abruptly varying layers necessary for advanced heterostructures, the clumsy liquid process proved incapable of the required nanometer-scale precision. To overcome these severe manufacturing bottlenecks, the industry was forced to transition toward advanced vapor phase methodologies, a shift catalyzed significantly by the pioneering research of Russell Dupuy in the late 1970s. Dupuy recognized the inherent limitations of liquid systems and dedicated his work to adapting metal organic chemical vapor deposition, MOCVD, a highly advanced technique originally derived from the silicon computer chip industry. In the MOCVD process, volatile metal organic precursor gases, such as trimethyl gallium, are mixed with highly reactive hydride gases and flowed uniformly over a heated substrate wafer within a tightly controlled vacuum chamber. The precursor molecules undergo rapid thermal decomposition only when they strike the heated surface of the wafer, depositing highly precise atomic layers of the semiconductor crystal gas atom by gas atom. Dupuy famously built his first successful MOCVD reactor primarily out of spare parts in a machine shop to prove his theory. His ultimate demonstration that this vapor technique could successfully grow high-purity, complex compound semiconductors with incredible layer precision completely revolutionized the industry. Teaming up with Nick Holonyak to publish their findings, Dupuy proved that MOCVD was vastly superior to older methods. It allowed for rapid, controllable, large-area wafer processing, effectively transitioning advanced diode designs from slow, bespoke laboratory curiosities into economically viable, mass-produced electronic components capable of powering the electronics boom of the late 20th century. Early commercial applications and market adoption. The commercialization of solid-state lighting began incredibly slowly, primarily due to exorbitant manufacturing costs and low production yields. In the early to mid-1960s, early red gallium arsenide devices were essentially bespoke scientific instruments, costing upwards of $200 per single unit. At such extreme price points, their use was strictly confined to high-budget aerospace equipment, military projects, and expensive laboratory testing gear. The transition to mass-market commercialization was spearheaded by an intense, fast-paced corporate rivalry between the Hewlett-Packard Optoelectronics division and the Monsanto Electronics Special Products division in the late 1960s. Monsanto, originally an industrial chemical supplier that manufactured and sold the raw gallium arsenide wafers to other tech companies, realized the immense untapped profit margins available in selling finished electronic devices. In 1968, under the aggressive guidance of visionary salesman and general manager George McLeod, Monsanto established a dedicated mass production facility in Palo Alto, California, right in the heart of what would become Silicon Valley. That same year, Monsanto launched the MAN-1, Monsanto Alphanumeric 1, cementing its place in history by producing the world's first commercial 7-segment numeric display. The MAN-1 was an intricate device. It consisted of 14 discrete semiconductor dies painstakingly hand-mounted onto a ceramic printed circuit substrate and encapsulated in a block of clear epoxy. By illuminating specific clusters of these dots, the display could generate numbers and crude letters, providing a solid-state alternative to fragile glass tubes. Hewlett-Packard responded aggressively to Monsanto's market entry by developing the competing 5082 7000 series display. This was a highly sophisticated 5x7 dot matrix display, utilizing 28 individual microscopic semiconductor dies. To gain a competitive edge, Hewlett-Packard equipped their display with a revolutionary onboard binary-coded decimal decoder driver circuit integrated directly into the package, drastically simplifying the electrical requirements for engineers looking to implement the display in their products. While initial prices for these displays remained astronomical, costing upwards of $55 per character in the early 1970s, the intense, cutthroat competition drove rapid innovation. This competition, coupled with the critical introduction of the planar manufacturing process and advanced packaging methods pioneered by John Horney at Fairchild Semiconductor, rapidly optimized fabrication yields, and by the mid-1970s, the cost per individual diode plummeted from hundreds of dollars to the matter of mere cents, effectively opening the floodgates for widespread integration into consumer electronics. One of the most culturally significant and highly publicized applications of early optoelectronics was the invention of the solid-state digital wristwatch. In May 1970, John Berge, the ambitious head of research and development at the Hamilton Watch Company based in Lancaster, Pennsylvania, appeared on The Tonight Show to demonstrate a functional prototype of a device called the Pulsar Time Computer. Conceived as a direct spin-off from the futuristic glowing digital clocks that Hamilton had been commissioned to build for Stanley Kubrick's 1968 cinematic masterpiece 2001: A Space Odyssey, the Pulsar was unlike any timepiece in human history. It featured absolutely no moving parts, no mechanical hands, no mainspring, and no ticking dial. Instead, it housed a blank, futuristic screen crafted from synthetic ruby that, upon the press of a side button, illuminated bright red digits to display the time. Host Johnny Carson, confronted with a watch that required the user to press a button just to see the time, famously dismissed the device. To Berge's absolute horror on national television, Carson declared it would never put Mickey Mouse out of business before tossing the delicate $1,500 gold prototype over his shoulder onto the studio floor. Despite Carson's harsh skepticism and the astronomical price tag, which Carson quipped would tell you the exact moment you went bankrupt, the commercial launch of the Pulsar P1 in 1972 sparked a technological sensation. The Pulsar established an entirely new category of consumer electronics, proving so popular that it prompted scores of American semiconductor firms to aggressively storm the traditional Swiss-dominated horology market. The internal architecture of the Pulsar was a breathtaking marvel of 1970s miniaturization, containing 44 integrated circuit chips and over 4,000 microscopic gold bonding wires linking the array of light-emitting dies provided by companies like Letronics. However, the Pulsar also starkly highlighted a fundamental technological limitation of early solid-state lighting: immense power consumption. The early red diodes required so much electrical current to achieve a visible brightness that illuminating the display continuously would entirely drain the miniature watch battery in a matter of hours. Consequently, Hamilton engineers were forced to implement a draconian power management compromise, wherein the screen remained entirely dark until the user actively pushed a button, which illuminated the time for a fleeting, precisely timed 1.25 seconds. While initially viewed as a charmingly futuristic novelty, consumers eventually found the two-handed push-to-read requirement highly cumbersome in daily life. By 1977, the relentless high power draw of the diodes led to the rapid obsolescence of the technology in wristwatches, as it was wholly supplanted by the vastly more power-efficient, constantly on liquid crystal display technology. The urgent requirement for small, reliable, and solid-state numerical readouts simultaneously triggered a profound revolution in the calculator industry. Prior to the 1970s, electronic calculators were massive desktop machines that relied on heavy, fragile, and high-voltage Nixie tubes, or early vacuum fluorescent displays. The Nixie tube, a glass bulb filled with neon gas and stacked wire mesh cathodes shaped like numbers, required upward of 170 volts to generate its characteristic orange glow, making battery-powered portability practically impossible. The introduction of low-voltage, highly shock-resistant semiconductor displays enabled the creation of the true pocket calculator. In the autumn of 1971, Bomar/Alley Incorporated released the Bomar 901B, which was popularly marketed and widely known as the Bomar Brain. Measuring roughly 5 by 3 inches and retailing for $240, it was the first widely successful American-made pocket calculator. It featured an 8-digit red display that consumed significantly less physical volume and electrical power than any earlier vacuum tube iteration, proving that complex mathematics could be carried in a shirt pocket. The following year, Hewlett-Packard completely revolutionized the professional and scientific market with the introduction of the legendary HP 35, the world's first handheld scientific calculator. The industrial design of the HP 35 was heavily constrained by the daunting necessity of fitting 35 distinct function keys and a massive 15-digit scientific notation display into a rigid pocket form factor. Because the semiconductor dies were still highly expensive to manufacture, HP engineers utilized ingenious optical engineering tricks to drastically minimize material costs. The individual digits were assembled from microscopic chips, some no larger than a grain of table salt. Because they were physically tiny, they emitted very little total light. To compensate for this without using larger, more expensive chips, the top of the protective plastic casing for each digit module was molded into a cylindrical bubble lens. These integrated optical magnifying lenses optically enlarged the appearance of the tiny illuminated segments, drastically enhancing readability while minimizing the physical volume of costly semiconductor material required. Even with these clever material optimizations, powering a 15-digit light array posed a formidable electrical engineering challenge. To achieve the mandated 4-hour continuous battery life, Hewlett-Packard utilized a 3-cell nickel-cadmium rechargeable battery pack. This pack was routed through a highly advanced single-transistor DC-to-DC converter designed by Chu Yen that operated at over 80% efficiency, ensuring the power-hungry diodes received adequate current to remain visible in bright sunlight without catastrophic power loss. By the mid-1970s, as global production scaled up and raw component prices dropped due to fierce competition, the cost of handheld calculators plummeted from hundreds of dollars to below $10, entirely democratizing computational technology for the general public. Beyond consumer novelties like watches and calculators, the inherent, unparalleled reliability of solid-state lighting made it highly attractive for critical industrial, infrastructural, and aerospace applications where equipment failure was unacceptable. In the mainframe computer industry of the 1960s and 1970s, complex operator consoles relied on hundreds of miniature indicator lights to convey system status, memory addresses, and error codes to programmers. Traditional incandescent bulbs generated substantial waste heat, drew excessive current, and suffered from notoriously short operational lifespans due to fragile, easily broken tungsten filaments. When IBM introduced the System 370 Model 145 in 1970, the very first commercial computer to use monolithic silicon chips for main memory rather than bulky, outdated magnetic iron ferrite core storage, it represented a holistic, industry-wide embrace of solid-state technology. Replacing failure-prone incandescent indicators with theoretically immortal light-emitting diodes reduced costly maintenance downtime and significantly lowered the thermal load on the computer's delicate, massive internal air conditioning systems. Similarly, the aerospace industry eagerly adopted the new technology to modernize aircraft cockpits and improve flight safety. Early analog aviation panels, often affectionately referred to by pilots as steam gauges, were densely packed with electromechanical dials and incandescent backlighting that required constant, expensive maintenance and frequent bulb replacement to ensure night flying capability. As aviation transitioned toward modern electronic flight instrument systems, or EFIS, colloquially known as glass cockpits, the integration of solid-state indicators provided unmatched vibration resistance and longevity. Furthermore, the incredibly narrow, precise spectral emission of semiconductors allowed engineers to design indicator panels with strict, standardized chromacity, reserving true red exclusively for critical life-threatening warnings, yellow for cautions, and green for normal operations. This reliability saw the technology rapidly cascade down into everyday infrastructure, becoming the standard for elevator floor indicators and massive multi-line telephone switchboard consoles. Manufacturing challenges, thermal management, and degradation. Despite their aggressive marketing as indestructible, everlasting cold light devices that would never burn out, early diodes were heavily plagued by insidious, hard-to-predict failure modes. These failures were primarily driven by the extreme difficulties of thermal mismanagement at the microscopic level. While they certainly did not generate the macroscopic radiant heat of an incandescent filament, which literally boils off tungsten to create light, the microscopic p-n junction within the semiconductor generated intense, highly localized heat. This heat was the unavoidable byproduct of non-radiative recombination, electrons and holes generating phonons instead of photons, and the inherent electrical resistance of the material itself. If this highly concentrated heat was not efficiently conducted away from the microscopic die into the surrounding metal lead frame or substrate, the internal junction temperature would escalate rapidly. Unlike traditional incandescent bulbs, which typically fail catastrophically and instantly when their brittle filament snaps, semiconductors undergo a much more frustrating process known as parametric failure. In parametric failure, the device does not stop working completely, rather its luminous efficacy steadily degrades over time, growing dimmer and dimmer until it is no longer useful. Extensive long-term testing by manufacturers demonstrated that operating a diode at a steady-state junction temperature approaching or exceeding 100 degrees Celsius caused a dramatic, non-linear acceleration of this lumen depreciation. This degradation was eventually traced to several distinct microscopic phenomena. At elevated operating temperatures, thermally activated interdiffusion occurs at the highly sensitive interfaces between the semiconductor crystal and the deposited metal contacts that supply the electricity. This interdiffusion significantly increases the series electrical resistance of the device, creating a highly destructive thermal feedback loop. Higher resistance leads to greater localized heating, which further fuels atomic diffusion, ultimately strangling the flow of electrons to the active recombination region and causing the light output to plummet. Consequently, the industry was forced to develop stringent thermal characterization standards and employ advanced thermal interface materials, heat-sinking substrates, and strict current-limiting circuits to ensure the promised 50,000-hour lifespans could actually be achieved in the real world. Another severe reliability issue in early optoelectronics stemmed not from the semiconductor crystal itself, but from the clear polymer resins used to encapsulate and protect the fragile dies and microscopic gold bonding wires. To create a rigid, transparent protective dome that also functioned as a refractive optical lens to focus the light, manufacturers overwhelmingly relied on clear liquid epoxy resins that were cured into hard plastics. However, early epoxy polymers were highly susceptible to a form of severe chemical degradation known as photooxidation. When exposed to external ultraviolet light from ambient sunlight, or when subjected to the prolonged internal heat generated by the diode itself, high-energy photons attack the chemical backbone of the polymer. Early commercial epoxies were predominantly aromatic-based, meaning their molecular structures contained stable but highly reactive benzene rings. When energetic photons strike these aromatic bonds, they physically cleave the polymer chains, generating highly reactive, unstable molecules known as free radicals. These free radicals readily and aggressively react with atmospheric oxygen slowly permeating the plastic housing, leading to the formation of entirely new molecular structures within the plastic, known as chromophores. These newly formed chromophores actively absorb wavelengths of light in the blue and green spectrum. Because the blue and green spectrum is absorbed within the plastic housing rather than passing through, the light escaping the device takes on a pronounced, permanent, and highly undesirable yellow or brownish hue. This yellowing effect severely altered the chromaticity of the emitted light, essentially rendering precise, color-coded aviation and industrial indicators useless over long operational periods, as a green light would slowly appear sickly yellow. Furthermore, the chemical breakdown of the polymer matrix caused the epoxy to become physically brittle. Combined with thermal cycling, this brittleness led to microcracking and the catastrophic delamination of the internal bonding wires, a failure known as the popcorn effect, which permanently severed the electrical circuit and killed the device. Overcoming this severe limitation required chemical engineers to entirely abandon cheap aromatic epoxies in favor of highly complex aliphatic resins and eventually advanced silicones, which were specifically formulated to be inherently immune to UV-induced free radical formation. The limitation to low power rolls, the missing blue photon. Despite the monumental leaps in manufacturing efficiency, brightness, and color availability achieved throughout the 1970s and 1980s, the light-emitting diode remained strictly relegated to the niche domains of indication, display, and signaling. The grand, world-changing vision proposed by Nick Holonyak in 1963 that the technology would rapidly displace the Edison bulb for general residential and commercial illumination was continually thwarted by the intractable physics of the electromagnetic spectrum. To achieve general illumination suitable for homes and offices, a light source must produce white light. White light is not a specific wavelength, rather a broad spectrum synthesis of multiple wavelengths spanning the entire visible range. In solid-state physics, generating white light requires one of two fundamental approaches. The first is additive color mixing, which requires the simultaneous operation of highly efficient red, green, and blue diodes placed in extremely close proximity. The second, vastly more commercially viable approach relies on utilizing a highly energetic short wavelength blue or ultraviolet diode to optically excite a chemical phosphor coating. The phosphor then fluoresces to produce a broad spectrum of secondary colors like yellow and red that combine with the blue emission to appear perfectly white to the human eye. Both of these pathways face a single insurmountable barrier: the absolute necessity of a high-brightness blue light-emitting diode. Blue photons possess the highest energy in the visible spectrum. To generate them, a semiconductor must possess an exceptionally wide band gap of approximately 2.6 to 3.4 electron volts. Throughout the 1970s and 1980s, identifying a material capable of sustaining such a wide band gap while simultaneously permitting the creation of a stable p-n junction completely confounded the world's greatest materials scientists. Initial research focused heavily on zinc selenide, a 2,6 semiconductor material that boasted an incredibly low lattice mismatch of just 0.3% with readily available gallium arsenide substrates, theoretically promising flawless, defect-free crystal growth. However, zinc selenide proved fundamentally unstable and highly susceptible to rapid, catastrophic structural degradation under the intense electrical fields required for operation. Conversely, the 3V semiconductor gallium nitride possessed the perfect direct band gap of 3.4 electron volts necessary for deep blue emission, but the material was notoriously and violently difficult to work with. No suitable crystalline substrate existed on Earth that matched its atomic spacing. Growing gallium nitride on the next best alternative, synthetic sapphire, resulted in a catastrophic 16% lattice mismatch. This severe geometric discrepancy caused the resulting crystal to be riddled with billions of microscopic threading dislocations per square centimeter. These defects acted as non-radiative recombination centers, utterly destroying the optical efficiency of the material. Furthermore, achieving reliable p-type doping in gallium nitride to create the necessary p-n junction was deemed chemically impossible for decades. Early attempts resulted in atrocious sheet resistances that required forward voltages in excess of 20 to 30 volts just to coerce a barely visible, highly inefficient blue glow, causing most major research laboratories, including RCA and Bell Labs, to entirely abandon the material. Consequently, the global optoelectronics industry was physically trapped in the lower energy, longer wavelength regions of the spectrum. Red, orange, yellow, and pale green devices flourished, but without the crucial highly energetic blue photon, the synthesis of white light was fundamentally impossible. It would take until the early 1990s and the eventual Nobel Prize-winning breakthroughs by Suji Nakamura, Isamu Asaki, and Hiroshi Amano in conquering gallium nitride epitaxy and discovering how to activate p-type doping using thermal annealing to finally shatter this multi-decade barrier, thereby unlocking the final prerequisite for the global solid-state lighting revolution. Gallium nitride breakthrough. The transition from traditional incandescent and fluorescent lighting to solid-state illumination represents one of the most profound technological and ecological shifts in modern engineering history. This monumental transition, which has fundamentally altered global energy consumption, urban infrastructure, and the design of advanced electronic displays, was catalyzed by a singular, elusive scientific achievement: the realization of the high-brightness blue light-emitting diode, or LED, in the early 1990s. The Royal Swedish Academy of Sciences recognized the sheer magnitude of this paradigm-shifting achievement by awarding the 2014 Nobel Prize in Physics to three pioneering researchers, Isamu Akasaki, Hiroshi Amano, and Shuji Nakamura. Their collective, relentless work dismantled the formidable material science barriers that had previously prevented the production of efficient blue light, which was the final missing prerequisite for generating pure white light and enabling full-color solid-state emissive displays. The scientific pursuit of the blue LED required a semiconductor material possessing a wide, direct band gap capable of emitting high-energy photons in the blue and ultraviolet regions of the electromagnetic spectrum. Gallium nitride, GaN, was identified as a theoretically ideal candidate due to its direct band gap of 3.4 electron volts, which directly corresponds to the precise wavelength of light in the ultraviolet and blue range. However, the practical application of gallium nitride was severely hindered by two seemingly insurmountable material science challenges that defined the research landscape of the early 1990s: the extreme difficulty of growing high-quality, defect-free gallium nitride crystals, and the apparent impossibility of creating functional p-type or positive hole-rich semiconductor layers within the material. The primary obstacle in gallium nitride crystal growth stemmed from the complete lack of a suitable native substrate upon which the crystals could be grown. Researchers were forced to rely on heteroepitaxy, specifically attempting to grow gallium nitride epitaxial layers on foreign sapphire substrates. This approach was deeply flawed because sapphire and gallium nitride possess a severe lattice mismatch and significant differences in their thermal expansion coefficients. When gallium nitride was deposited directly onto the sapphire, This mismatch resulted in catastrophic structural defects, massive dislocation densities, and microscopic cracks that utterly destroyed the crystal's optical properties, rendering the material completely useless for efficient photon emission. The initial breakthrough in overcoming this fundamental lattice mismatch occurred through the collaborative work of Isamu Akasaki and his doctoral student Hiroshi Amano at Nagoya University. They pioneered the revolutionary low-temperature buffer layer technology. By depositing a very thin layer of aluminum nitride, ALN, on the sapphire substrate at exceptionally low temperatures before growing the primary gallium nitride layer, they successfully accommodated the immense physical strain between the mismatched crystalline structures. This buffer layer acted as a structural and atomic bridge, drastically reducing the defect density and allowing for the subsequent growth of high-quality specular gallium nitride crystals with significantly improved optical and electrical characteristics. Simultaneously, Shuji Nakamura, working independently as a dedicated researcher at Nichia Corporation, pursued a different but equally revolutionary approach to the crystal growth problem. Nakamura recognized that conventional metal-organic chemical vapor deposition (MOCVD) reactors, which were the industry standard for semiconductor fabrication, were highly unstable for gallium nitride growth. The extreme temperatures required for the process created aggressive thermal convection currents near the heated substrate, which literally blew the reactant gases away before they could deposit uniformly. Over the course of 18 grueling months of iterative engineering and daily modifications, Nakamura invented a completely novel reactor architecture that he named the two-flow MOCVD system. This ingenious mechanical design introduced a secondary vertical subflow of inactive carrier gas that pushed downward against the primary horizontal flow of reactant gases. The subflow gently but firmly compressed the reactive mixture against the heated sapphire substrate, suppressing the disruptive thermal boundary layer and preventing the premature convection of the precursor gases. This breakthrough in fluid dynamics and reactor geometry allowed Nakamura to consistently and reproducibly grow exceptionally uniform, high-quality gallium nitride films across the entire surface of the substrate at a very low carrier gas velocity, setting the definitive stage for complex device fabrication. With high-quality crystals successfully synthesized, the researchers faced the second monumental hurdle, achieving reliable p-type conductivity. A functional light-emitting diode inherently requires a p-n junction, a precise interface where an n-type layer, which is rich in negatively charged electrons, meets a p-type layer, which is rich in positively charged holes. When an electrical voltage is applied, it drives these charge carriers into a central active region where they recombine, releasing their energy in the form of photons. While N-type gallium nitride was relatively straightforward to produce, all early attempts to dope gallium nitride with magnesium to create the necessary p-type layers consistently ended in failure. The magnesium-doped layers remained highly resistive, functioning essentially as insulators rather than conductors, and exhibited absolutely no functional hole conductivity. The resolution to this perplexing p-type doping mystery began to unfold with an accidental but highly observant discovery by Isamu Akasaki and Hiroshi Amano in 1989. While analyzing their magnesium-doped gallium nitride samples under the intense beam of a scanning electron microscope, they noticed a peculiar phenomenon. The specific microscopic regions that were exposed to the electron beam unexpectedly exhibited vastly increased luminescence and localized p-type conductivity. This process, which became known as low-energy electron beam irradiation, or LEBE, successfully activated the magnesium acceptors, allowing Akasaki and Amano to demonstrate the world's first functional, albeit highly localized, gallium nitride p-n junction. However, the Libby method was profoundly flawed for commercial manufacturing. It was highly localized, incredibly inefficient, restricted to the immediate surface of the material, and completely unsuitable for mass production. Furthermore, the underlying physical mechanism of why the electron beam worked remained a total mystery. It was Shuji Nakamura who in 1992 successfully unraveled the deep solid-state physics behind the p-type doping failure and the Libby phenomenon. Nakamura theorized and subsequently proved that the fundamental problem was rooted in a process known as hydrogen pasteurization. During the MOCVD process, ammonia was heavily utilized as the primary source of nitrogen. The extreme thermal decomposition of this ammonia released abundant hydrogen atoms directly into the highly reactive chamber. Nakamura discovered that these tiny hydrogen atoms were diffusing deep into the gallium nitride crystal lattice and chemically bonding with the introduced magnesium dopants, thereby forming neutral magnesium-hydrogen complexes, effectively pasteurizing the magnesium and preventing the atoms from acting as electron acceptors, thereby destroying the material's p-type conductivity. To break these incredibly resilient atomic bonds, Nakamura developed a brilliantly simple yet highly effective thermal annealing process. By subjecting the magnesium-doped gallium nitride wafers to high temperatures ranging from 400 to 700 degrees Celsius in a strictly nitrogen-rich, hydrogen-free atmospheric ambient, the applied thermal energy physically severed the magnesium-hydrogen bonds. The liberated hydrogen subsequently out-diffused from the crystal lattice, leaving behind electrically active magnesium acceptors and permanently establishing highly conductive p-type gallium nitride across the entire wafer. This theoretical clarification of the hydrogen passivation mechanism, combined with the practical thermal annealing technique, finally allowed for the reliable mass production of uniform p-type layers. The ultimate culmination of these extraordinary material science breakthroughs occurred when Akasaki, Amano, and Nakamura integrated their high-quality crystals and functional PN junctions with sophisticated double heterostructure designs. By carefully inserting a very thin, active layer of indium gallium nitride, INGN, sandwiched squarely between wider bandgap layers of aluminum gallium nitride, ALGN, they created a quantum well structure. This structural architecture effectively trapped the electrically injected electrons and holes in a confined physical space, forcing them to recombine with phenomenal radiative efficiency. In 1993, the synthesis of these discoveries resulted in the public demonstration of the world's first ultra-bright, high-efficiency blue light-emitting diode, a technological triumph that entirely redefined the boundaries of applied physics. The development of the blue LED also generated significant historical and cultural ripples, particularly regarding the corporate treatment of inventors. Shuji Nakamura's breakthrough at Nikkei Corporation eventually culminated in a landmark, highly publicized legal battle that profoundly impacted Japanese corporate culture and intellectual property law. Despite generating an invention that catalyzed a multi-billion-dollar global industry, Nakamura initially received a mere 20,000 Japanese yen, equivalent to less than 200 United States dollars, as a standard corporate bonus for his world-changing patent. After leaving Nikkei to accept a professorship at the University of California, Santa Barbara, Nakamura sued his former employer in 2001, claiming that his unique individual ability and determination were responsible for the patent's success, and that he was rightfully entitled to a fair share of the astronomical profits. The case drew massive international attention, with foreign researchers and media notoriously dubbing him Slave Nakamura, to highlight the disparity between his monumental contribution and his meager corporate compensation. In a shocking initial verdict in 2004, the Tokyo District Court ruled in Nakamura's favor, recognizing his contribution to the invention at 50% and ordering Nikkei to pay him 20 billion yen, or roughly $189 million, which was the highest sum ever awarded to an employee inventor in Japanese history. Although this astronomical figure was later reduced by the Tokyo High Court in 2005 to a comprehensive settlement of 840 million yen, or roughly $8.1 million, the lawsuit served as a massive catalyst for change. It forced the notoriously rigid Japanese corporate system, which traditionally relied on lifetime employment and minimal individual recognition, to fundamentally reevaluate and reform how it compensated highly innovative researchers and engineers, sparking a wave of updated patent laws and corporate reward structures across the nation's high-technology industries. The genesis of white light. The perfection of the high-brightness blue LED by Nakamura, Akasaki, and Amano was a watershed moment in the history of technology. It was celebrated not merely because it finally completed the primary color triad of red, green, and blue required for full-color digital displays, but fundamentally because it served as the required optical engine for generating high-quality white light. The engineering behind the first solid-state white LEDs required a massive conceptual shift in optical physics, moving away from discrete semiconductor emission and pivoting toward the highly sophisticated manipulation of photoluminescence. The genesis of solid-state white light was driven by an urgent multi-billion-dollar commercial mandate to replace wildly inefficient heat-generating incandescent bulbs with a reliable, durable, and radically energy-efficient semiconductor alternative. Initially, engineers attempted to create white light through the most direct method available, spatial color mixing. This involved combining discrete red, green, and blue LED chips within a single physical package. By utilizing complex microprocessors to precisely modulate the electrical current supplied to each individual chip, the three distinct wavelengths could be optically mixed to deceive the human visual cortex into perceiving pure white light. While this method offered the distinct advantage of dynamic color tunability, allowing users to shift the hue on demand, it presented severe commercial, thermodynamic, and optical limitations. From a manufacturing perspective, aligning and packaging three separate semiconductor dies into a single fixture was prohibitively expensive and highly complex. Furthermore, because red, green, and blue LEDs degrade significantly differently over time, the carefully calibrated white light would inevitably shift and discolor as the device aged. Most critically, however, the resulting mixed light suffered from exceptionally poor color rendering capabilities. Because the RGB approach relied on three extremely narrow, spiked bands of wavelength emission, it completely failed to provide a broad, continuous spectral distribution necessary to accurately illuminate objects in the physical world. This resulted in a harsh, unnatural color representation that washed out subtle hues and was entirely unsuitable for general residential or commercial illumination, where high-fidelity color accuracy is paramount. To overcome these insurmountable optical limitations, the lighting industry aggressively pivoted toward a methodology known as phosphor conversion, a technique that was heavily reliant on the incredible power and efficiency of the newly invented blue INGN LED. In September 1996, Nikkei Corporation, leveraging its total mastery of blue LED technology, successfully commercialized the world's first practical pseudo-white LED, carrying the historic product designation NSPW310AS. The engineering principle underlying this monumental breakthrough was an elegant solid-state application of the Stokes shift, a phenomenon involving the absorption and subsequent re-emission of light at a longer wavelength. Nikkei engineers began with a highly efficient blue indium gallium nitride LED chip, which emitted high-energy blue light at a peak wavelength of approximately 465 nanometers. They completely encapsulated this microscopic blue dye within a synthetic protective resin that was carefully infused with a very specific microscopic luminescent powder, yttrium aluminum garnet heavily doped with cerium, universally denoted in material science as YAG.Ce. When the blue LED was energized by an electrical current, it flooded the encapsulating resin with billions of high-energy blue photons. As these photons collided with the complex cerium-doped garnet crystalline structure, a precisely calculated portion of the blue light was absorbed by the phosphor material. This absorption excited the electrons within the cerium ions, kicking them into a higher, unstable energy state. Within nanoseconds, as these excited electrons relaxed back to their stable ground state, they re-emitted the absorbed energy as lower energy photons. Due to the specific atomic structure of the YAG:Ce material, this re-emitted light fell broadly across the yellow and green regions of the visible electromagnetic spectrum. Crucially, the manufacturing process required immense precision. The phosphor coating had to be engineered to be partially translucent. This deliberate translucency allowed a highly specific percentage of the original, unabsorbed blue photons to pass directly through the resin without ever interacting with the phosphor particles. The resulting optical output of the entire package was a simultaneous overlapping emission of unabsorbed high-energy blue light and down-converted broad-spectrum yellow light. Because blue and yellow act as complementary colors in human visual perception, the optical mixing of these two distinct light sources simultaneously stimulated the short, medium, and long wavelength photoreceptors in the human retina, creating the highly convincing illusion of pure white light. This phosphor conversion methodology was utterly revolutionary for the lighting industry because it required only a single semiconductor chip and a simple electrical driver, vastly reducing manufacturing complexity, dramatically lowering production costs, and streamlining the thermal management architecture of the device. However, the initial generation of YAG:Ce white LEDs, while commercially viable, was not without significant optical flaws. The emission spectrum of this rudimentary blue-yellow combination possessed two massive spectral peaks, but suffered from severe gaping deficiencies in the deep red and cyan regions of the spectrum. Consequently, these early white LEDs produced a harsh, clinical, and excessively cool light. They typically possessed a highly elevated correlated color temperature, CCT, exceeding 4,000 Kelvin, and a mediocre color rendering index, CRI, hovering between 70 and 80, making objects appear slightly washed out or bluish. While this cool, efficient white light was perfectly adequate for utilitarian applications, such as flashlights, industrial indicator lights, and the burgeoning market for liquid crystal display backlighting, it was largely rejected by mainstream consumers for residential environments. In homes, restaurants, and hospitality venues, the warm, red-enriched, comforting glow of traditional incandescent bulbs, which typically operate around 2700 Kelvin, was heavily preferred. Early attempts by chemists to artificially redshift the emission of the YAG garnet by substituting the yttrium atoms with gadolinium, or substituting aluminum with magnesium and silicon, resulted in a catastrophic loss of quantum efficiency, particularly when the LED package heated up during sustained operation. This critical market limitation catalyzed a massive, fiercely competitive global research initiative into novel, high-performance phosphor compositions capable of broadening the emission spectrum and significantly lowering the correlated color temperature to achieve genuine, warm white light. The true breakthrough in color quality occurred with the transition away from traditional oxide-based garnets and toward highly complex, difficult-to-synthesize nitride and oxynitride compositional spaces. Material scientists discovered that incorporating nitrogen directly into the host lattice of the phosphor offered profound chemical advantages. Because nitrogen possesses a significantly lower electronegativity than oxygen, it effectively lowered the energy levels of the doped activator ions, specifically divalent europium. This allowed the newly engineered phosphors to far more effectively absorb the blue LED radiation and emit deeper into the longer wavelength regions of the spectrum. Pioneering work by global research teams led to the discovery of europium-doped silicon-aluminum oxynitride phosphors, as well as complex calcium-aluminum-silicon nitride materials, which exhibited absolutely extraordinary luminescent properties. These advanced nitride-based phosphors could efficiently emit deep red, amber, and vibrant orange wavelengths, while miraculously maintaining incredibly high quantum efficiencies exceeding 85% even at the extreme, localized temperatures that routinely exceed 200 degrees Celsius within a high-power LED package. By moving away from single phosphor solutions and instead carefully blending these advanced red-emitting nitride phosphors with the traditional yellow-emitting YAG garnets and highly stable green-emitting oxynitrides, engineers were able to completely fill in the spectral gaps of the original blue LED pump. This precise, highly controlled chemical tuning birthed the modern, high-fidelity, high-color rendering white LED. Today, sophisticated solid-state lighting packages utilize complex proprietary cocktails of these advanced nitride and oxynitride phosphors to produce a continuous, rich, broad-spectrum light that is virtually indistinguishable from natural sunlight or legacy incandescent sources. These modern packages routinely achieve color rendering indices well above 90, accurately rendering deep reds and subtle skin tones. The successful synthesis and commercialization of these robust, high-temperature stable luminescent materials fundamentally solved the early color quality crisis, finally allowing phosphor-converted white LEDs to move beyond simple indicator lights and aggressively dominate the massive global market for general interior and exterior illumination. However, the pursuit of absolute lighting efficiency across the entire visible spectrum highlighted a lingering, deeply perplexing phenomenon in semiconductor physics known universally as the green gap. While indium gallium nitride excels at producing highly efficient blue light, and aluminum gallium indium phosphide is highly efficient at generating red and amber light, the external quantum efficiency of both material families plummets catastrophically when engineered to emit light in the green and yellow-green spectrum, specifically between 535 and 570 nanometers. This is particularly problematic because the human eye is biologically most sensitive to green light, making it theoretically the most important wavelength for highly efficient luminous efficacy. The physics behind the green gap are staggeringly complex. As engineers increase the indium content within the indium-gallium quantum wells to stretch the emission wavelength from blue to green, the physical lattice mismatch between the indium-gallium layers and the surrounding gallium nitride barriers becomes extreme. This massive internal strain generates massive piezoelectric polarization fields within the Wurtzite crystal structure of the semiconductor. These intense internal electric fields physically pull the negatively charged electrons and the positively charged holes in opposite directions within the quantum well, drastically reducing their spatial overlap. This phenomenon, formerly known as the quantum confined Stark effect, severely decreases the probability that the electrons and holes will successfully recombine to emit a photon, plunging the radiative efficiency of the device at high power. Furthermore, high indium content layers suffer from severe compositional fluctuations, creating localized defects that act as non-radiative recombination centers, where energy is lost as useless heat rather than light. This fundamental material challenge is heavily compounded by a secondary phenomenon known as efficiency droop. Regardless of the wavelength, the internal quantum efficiency of nitride-based LEDs drastically falls as the electrical drive current is cranked up to the high levels required for general illumination and automotive headlights. Researchers widely attribute this droop to Auger recombination, a complex non-radiative process where the energy from a recombining electron-hole pair is transferred to a third charge carrier instead of generating a photon, effectively capping the maximum brightness and efficiency of the device at high power. To combat the green gap and efficiency droop, contemporary material scientists are heavily exploring highly advanced nanostructures, such as hybrid multi-quantum wells, trapezoidal well designs, and the growth of GaN on nonpolar and semipolar crystalline planes. These advanced geometries are specifically designed to artificially screen or entirely eliminate the strain-induced piezoelectric fields, thereby mitigating the quantum-confined Stark effect and forcing the electrons and holes back together. Solving the green gap remains one of the holy grails of solid-state physics, as highly efficient direct green emission would eliminate the reliance on energy-converting phosphors entirely, paving the way for ultra-efficient, pure RGB white light mixing and next-generation hyper-bright emissive displays. Solid-state lighting revolution. The maturation of high-brightness, high-fidelity phosphor-converted white LEDs ignited a sweeping, unprecedented technological revolution that fundamentally disrupted a century-old lighting industry. This revolution has dictated massive, permanent shifts in global energy policy, redefined architectural management of urban infrastructure, and completely transformed the aesthetics and safety mechanisms of modern automotive engineering. This solid-state lighting revolution was entirely propelled by the staggering thermodynamic and quantum efficiency of the LED architecture. Traditional incandescent light bulbs, the bedrock of global illumination since the late 19th century, operated by passing an electrical current through a fragile tungsten filament until it became white-hot. This process, relying entirely on black-body radiation, was inherently and catastrophically wasteful. It converted barely 5% of the consumed electrical energy into useful visible light, while aggressively radiating the remaining 95% into the surrounding environment as useless parasitic infrared heat. Compact fluorescent lamps, CFLs, improved upon this abysmal efficiency, but they still relied on fragile glass tubes, high-voltage gas discharges, and the mandatory inclusion of highly toxic mercury vapor on disposal. In stark, revolutionary contrast, light-emitting diodes completely bypass the need for superheated filaments or toxic gases. They convert electrons into photons directly within the microscopic, solid-state lattice of a semiconductor crystal. This highly controlled, non-thermal emission process allows high-quality LED lamps to consume a staggering 75 to 90% less energy than comparable incandescent lamps, while simultaneously offering an operational lifespan that routinely exceeds 25,000 continuous hours, drastically outlasting legacy technologies by a factor of 25 to 100. The macroeconomic and environmental implications of this extreme efficiency are profound. Historically, general illumination accounted for approximately 15 to 20% of the world's total electricity consumption, representing a massive continuous source of global greenhouse gas emissions. Recognizing the unprecedented, immediate energy conservation potential of solid-state technology, governments and regulatory bodies worldwide initiated aggressive, coordinated legislative campaigns to permanently phase out and eventually ban entirely the manufacture and importation of legacy lighting technologies. The European Union served as an early regulatory pioneer. Beginning in September 2009, the EU implemented a strict, multi-tiered eco-design directive that progressively eliminated the worst-performing incandescent bulbs from the market. This phased ban escalated over several years, eventually restricting the sale of highly inefficient halogen spotlights and culminating in a comprehensive mandate to eliminate virtually all fluorescent lighting by 2023, citing both energy inefficiency and the environmental hazards of mercury under the Restriction of Hazardous Substances Directive. Similar highly aggressive elimination strategies were adopted across the globe. Australia was one of the earliest adopters, announcing a phase-out of incandescent bulbs in 2007 that was completed by 2010, closely followed by nations like Brazil, which systematically banned incandescent bulbs of varying wattages between 2012 and 2016. In India, the transition was accelerated not just by bans, but by massive proactive government intervention. In 2014, the Indian government launched the Ujjala, Unnat Jyoti by Affordable LEDs for All program, arguably the world's largest zero-subsidy LED distribution initiative. Utilizing a public sector company to bulk procure LEDs through highly competitive bidding, the program bypassed traditional, highly marked-up retail supply chains. This allowed the government to distribute over 270 million highly affordable LEDs directly to households, fundamentally shifting consumer behavior overnight, driving down the unit cost of LEDs globally and rapidly accelerating the obsolescence of incandescent technology in the developing world. In the United States, the legislative battle was protracted, spanning over 16 years of debate regarding consumer choice and government overreach. However, the transition became inevitable, and in 2023, the United States Department of Energy enacted a comprehensive binding rule that indirectly prohibited the sale and manufacture of general service lamps producing less than 45 lumens per watt. Since incandescent bulbs top out at roughly 15 lumens per watt, this mandate effectively sealed the fate of the traditional incandescent bulb in the North American market, a move the DOE estimated would save American consumers nearly $3 billion annually on utility bills, while massively cutting carbon emissions. This aggressive regulatory environment and rapid technological shift forced a violent existential pivot within the traditional corporate giants of the lighting industry. Companies that spent a century manufacturing disposable, high-volume glass bulbs were suddenly forced to reinvent themselves as high-technology electronics and software firms. Philips Lighting, the world's largest producer of lighting products, made a massive strategic pivot as early as 2006, deciding to aggressively move away from incandescent bulbs, which at the time constituted nearly two-thirds of their sales volume, in favor of scaled-up intensive LED production. Recognizing the extreme longevity of LEDs would ultimately cannibalize the traditional business model of repeatedly selling replacement bulbs, Philips completely restructured its corporate identity. In 2016, the lighting division was formally spun off from the parent electronics company, and in 2018 it rebranded entirely as Signify. This name change was deeply symbolic, reflecting the company's new strategic vision that light was no longer merely a utility for illumination, but an intelligent language capable of connecting devices and conveying digital meaning. To survive in a market where light bulbs no longer burn out, Signify and other industry leaders pioneered innovative circular economy business models, most notably Light as a Service, or LaaS. Under the LaaS framework, commercial and public sector customers no longer purchase lighting hardware. Instead, they pay a monthly or annual subscription fee for the provision of light itself. Signify retains total ownership of all the physical luminaires, sensors, and network controls, taking full responsibility for the design, installation, operation, and ongoing maintenance of the system. This fundamentally aligns the manufacturer's incentives with environmental sustainability. Because Signify owns the hardware, they are financially motivated to manufacture highly durable, modular, and exceptionally energy-efficient equipment that can be easily repaired, upgraded, or recycled at the end of its life cycle. High-profile implementations of this model, such as Signify's partnerships with global giants like ArcelorMittal and Nexans, demonstrate how LaaS frees up capital for businesses, guarantees immediate energy savings with zero upfront investment, and massively accelerates the deployment of connected smart LED infrastructure across the commercial sector. As commercial and consumer markets rapidly transitioned, the most dramatic, highly visible, and economically impactful applications of the LED revolution occurred within the realm of municipal infrastructure and urban planning. Street lighting has historically been one of the absolute largest utility expenses for local governments worldwide. For decades, municipalities were heavily reliant on high-pressure sodium and mercury vapor lamps, which cast a murky, monochromic, color-distorting orange or sickly green glow, consumed massive amounts of electricity, and required constant, highly expensive physical maintenance by municipal crews. The city of Los Angeles served as an incredibly important, massive early proving ground for municipal LED retrofitting. Beginning in July 2009, the city undertook a monumental, highly ambitious project to replace over 140,000 aging high-pressure sodium streetlights with advanced, custom-engineered LED fixtures. The engineering and economic results were nothing short of staggering. The massive transition reduced the city's streetlight energy consumption by over 60%. This translated to an extraordinary annual energy reduction of nearly 68,000 megawatt-hours, simultaneously eliminating over 40,000 tons of carbon dioxide emissions annually and saving local taxpayers approximately $10 million every single year in combined electricity and maintenance costs. Furthermore, the physical architecture of the LED chip provided a massive advantage in optical control. Unlike highly omnidirectional gas discharge lamps that blast light in all directions, LEDs are highly directional point sources. This allowed municipal engineers to design highly sophisticated, custom-molded polymer lenses and microreflectors that directed the light precisely onto the roadway and pedestrian sidewalks where it was needed. This drastically reduced the amount of light trespassing into residential bedroom windows and aggressively minimized upward light spillage into the night sky. This optical precision heavily contributed to stringent dark sky compliance initiatives, aiding in the critical abatement of urban sky glow, which severely disrupts nocturnal ecosystems, migratory bird patterns, and astronomical observations. However, the municipal transition to LEDs catalyzed a secondary, even more profound technological evolution, the birth of the connected smart city. Because LEDs are inherently solid-state electronic components driven by direct current, they can be seamlessly integrated with digital microprocessors, wireless network communication modules, and a vast array of environmental sensors. High-end architectural and municipal lighting systems are no longer static, isolated sources of illumination. They are highly dynamic, deeply connected, and hyper-intelligent nodes operating within the sprawling Internet of Things, or IoT. Modern smart lighting poles are routinely equipped with sophisticated sensory suites designed to monitor real-time traffic density, measure localized air quality and particulate matter, and track pedestrian flow dynamics. These highly intelligent systems utilize edge computing to analyze incoming data and autonomously optimize energy consumption in real time. For example, an intelligent street lighting system can autonomously dim its output to 20% capacity during quiet, deserted early morning hours to save power, and instantly, imperceptibly ramp up to full, brilliant brightness the millisecond a vehicle or pedestrian is detected by the integrated radar or optical sensors. This data-driven, highly adaptive approach not only maximizes absolute energy efficiency, routinely achieving up to 80% energy savings compared to traditional systems, but it also allows urban planners to leverage massive troves of predictive analytics to manage infrastructure, dispatch emergency services, and enhance public safety with unprecedented real-time granularity. The solid-state revolution similarly transformed the highly competitive field of automotive engineering, where exterior lighting rapidly evolved from a purely functional, highly regulated safety requirement into a sophisticated mechanism of active vehicle communication, dynamic safety enhancement, and aggressive brand identity. The integration of LEDs into automotive design began modestly and purely functionally in the early 1990s with the introduction of high-mount center brake lights. LEDs were prized for this specific application due to their instantaneous microsecond illumination times, which measurably improved the reaction speeds of following drivers compared to the slow thermal ramp-up time of traditional incandescent bulbs. By the mid-2000s, as the luminous efficacy of white LEDs improved drastically, luxury manufacturers began integrating high-intensity white LEDs into daytime running lights, or DRLs. The seminal moment for full exterior LED integration occurred in 2006 when Lexus introduced the LS600H, which achieved historical distinction as the world's first production vehicle to utilize LED arrays for its primary low-beam headlights. Because LED arrays generate significantly less forward-radiating infrared heat than halogen or xenon high-intensity discharge lamps, and because the individual diodes are incredibly small, automotive designers were suddenly liberated from the massive bulbous reflector housings of the past. They began utilizing the compact nature of the diodes to sculpt incredibly sleek, ultra-narrow, and highly aggressive headlight geometries that were physically impossible to achieve with legacy lighting technology, turning the headlight into a profound signature of brand identity. As thermal management techniques and semiconductor luminous efficacy continued to improve exponentially, automotive engineers pushed the technology further, developing highly advanced adaptive high-beam axis systems that utilize staggeringly complex matrix LED architectures. In a modern matrix LED headlight, the primary illumination source is not a single powerful bulb, but a densely packed, highly engineered array of hundreds or even thousands of individually addressable micro-LEDs, often paired with thousands of microscopic digital mirrors. This cutting-edge matrix system operates in continuous real-time synchronization with the vehicle's forward-facing stereoscopic cameras, radar, and LiDAR sensors. When the onboard camera system detects the headlights of an oncoming vehicle or the red taillights of a leading car in the same lane, the Lighting Matrix Manager, a dedicated high-speed microprocessor, processes the spatial data in a matter of milliseconds. Instead of dropping the entire headlight system to a low beam state and plunging the driver into relative darkness, the microprocessor selectively deactivates or heavily dims only the specific individual LED pixels whose light rays would directly strike the detected vehicle. This incredible pixel-level digital control creates a highly dynamic, precisely targeted shadow box or dark tunnel that perfectly tracks the moving vehicle in real time. This prevents any blinding glare for other drivers, while simultaneously maintaining maximum intense high-beam illumination on the surrounding road, shoulder, street signs, and peripheral environments. This technology fundamentally resolves the century-old historical trade-off in automotive lighting between maximizing long-distance visibility for the driver and preventing hazardous glare for oncoming traffic. Pushing the physical boundaries of solid-state photonics even further, premium manufacturers like Audi and BMW have introduced incredibly advanced laser lighting technology, specifically designed for ultra-high-speed nighttime driving scenarios. By firing a highly concentrated array of intense blue laser diodes through a tiny, precisely engineered phosphorus converter within the headlight housing, the system generates an incredibly brilliant, tightly focused, and highly collimated beam of pure white light. Identifiable by a distinct blue hue within the physical housing, this laser-assisted beam can effectively double the illumination range of even the most advanced standard LED high beams. By projecting clear, daylight-quality light up to 600 meters down the highway, laser headlights afford drivers critical, life-saving extra seconds to to detect and react to obstacles or sudden changes in driving conditions at high velocities. Simultaneously, the pervasive global adoption of solid-state lighting has sparked intense, highly consequential scientific inquiry into the concept of human-centric lighting, or HCL, and its profound, measurable biological impacts. As modern human populations spend increasingly vast majorities of their time, often upwards of 90%, living, working, and learning in artificially lit indoor environments, the specific spectral composition of those environments has rapidly emerged as a critical public health variable. Rigorous scientific consensus confirms that the human eye contains a highly specialized, recently discovered class of photoreceptors known as intrinsically photosensitive retinal ganglion cells, or IPRGCs. Crucially, these specific cells do not contribute to visual image formation. Instead, they act as highly sensitive environmental light meters that directly communicate with the suprachiasmatic nucleus of the brain, regulating the body's internal biological clock, or circadian rhythm. These non-visual biological pathways are highly, disproportionately sensitive to short wavelength radiation, specifically the high-energy blue light that is prominently featured in the emission spectrum of most standard white LEDs. When the human eye is exposed to this blue-enriched light, it triggers a powerful biological response that drastically suppresses the pineal gland's secretion of melatonin, the hormone responsible for inducing sleep. During the day, this suppression is highly beneficial. Clinical studies have demonstrated that exposing students and office workers to blue-enriched, high-color temperature lighting significantly promotes alertness, elevates mood, reduces fatigue, and measurably enhances cognitive processing speeds and concentration. However, this exact same biological mechanism becomes highly detrimental after sunset. If individuals are heavily exposed to the intense blue spectral spikes emitted by standard LEDs, smartphone screens, and televisions during the evening hours, it leads to severe circadian misalignment. The brain is tricked into believing it is still midday, resulting in the aggressive suppression of natural melatonin production, leading directly to sleep deprivation, insomnia, and a cascade of associated metabolic and psychological disorders. Medical researchers paralleled this biological disruption to the negative health impacts observed during the biennial shift to daylight savings time, where acute circadian misalignment leads to statistically significant increases in stroke, obesity, and cardiovascular events. In direct response to this growing public health concern, the commercial lighting industry has engineered highly sophisticated, dynamically tunable human-centric lighting systems. By utilizing complex multi-channel LED arrays that independently mix varying ratios of cool white, warm white, deep red, and specific cyan diodes, these IoT-enabled smart systems can smoothly and dynamically adjust both their color temperature and absolute intensity throughout the course of the day. These intelligent systems are programmed to artificially simulate the natural, shifting progression of the sun. They provide high-intensity, heavily blue-rich light at high noon to actively stimulate productivity and alertness in the workplace, and autonomously, imperceptibly transition to dim, warm, heavily red-dominant spectrums in the late afternoon and evening to facilitate the body's natural melatonin production and prepare the neurological system for restful sleep. This profound convergence of human endocrinology, software analytics, and solid-state physics underscores how the LED revolution has moved far beyond the simple provision of illumination, actively evolving into a technology designed to directly engineer and optimize the physiological and psychological well-being of the modern built environment. The precise spectral tunability of LEDs has triggered a massive revolution in global agriculture, specifically within the booming sector of controlled environment agriculture and vertical farming. Traditional agriculture is highly vulnerable to unpredictable weather, seasonal limitations, and geographic constraints. By moving crop production entirely indoors into highly regulated, climate-controlled environments, farmers can grow food year-round. However, indoor plants require massive amounts of light for photosynthesis. Traditional high-pressure sodium greenhouse lamps run incredibly hot and consume vast amounts of electricity, heavily threatening the economic viability of indoor farms. Solid-state horticultural LEDs solve this systemic issue through their incredible thermal efficiency and spectral precision. Because LEDs operate at vastly cooler temperatures than legacy lamps, they can be placed mere inches away from the plant canopy without scorching the delicate leaves. This close canopy strategy maximizes photon absorption and drastically reduces the energy required to illuminate the crop. Furthermore, plants do not utilize the entire spectrum equally. They primarily rely on specific wavelengths of deep red and royal blue light to drive photosynthesis and regulate morphology. Horticultural LED fixtures are custom-engineered to emit only these highly specific biologically active wavelengths, eliminating the massive energy waste associated with producing green and yellow light that plants largely reflect. By precisely manipulating the light spectrum, often referred to as a light recipe, growers can artificially trigger specific biological responses, dictating the plant's height, accelerating flowering cycles, increasing nutritional density, and maximizing overall crop yield. As global populations surge, available arable land decreases, and the effects of climate change disrupt traditional farming, this LED-driven vertical farming technology is rapidly emerging as a critical, highly sustainable pillar of future global food security. Beyond visible light, the continuous advancement of solid-state physics has extended the LED revolution deep into the ultraviolet spectrum, specifically with the development of ultraviolet C LEDs. For decades, industrial sterilization, municipal water purification, and medical decontamination have relied heavily on low-pressure mercury vapor lamps to generate the highly energetic UVC light required to penetrate cell walls and aggressively deactivate the DNA and RNA of harmful pathogens, bacteria, and viruses. However, these legacy mercury lamps are incredibly fragile, require long warm-up times, consume massive amounts of power, and present a severe toxic hazard to the environment and human health if broken. The emergence of UVC LEDs, primarily constructed from highly complex aluminum gallium nitride semiconductor alloys, presents a massive technological upgrade. UVC LEDs contain absolutely zero toxic mercury, are incredibly durable, and can be switched on and off instantaneously without degrading their lifespan. They are rapidly being adopted to replace mercury lamps in critical applications, ranging from municipal water treatment facilities to the rapid cold curing of industrial adhesives, inks, and coatings in advanced manufacturing environments. While the external quantum efficiency of deep UV LEDs currently remains significantly lower than their visible light counterparts due to extreme challenges in crystal growth and light extraction, rapid material science advancements, including the development of novel superlattice structures, are steadily lifting their performance, heralding the eventual end of the toxic mercury lamp era. Finally, the ubiquitous deployment of high-speed LED lighting infrastructure has given rise to an entirely new paradigm of wireless data transmission known as light fidelity, or Li-Fi. As the global demand for wireless communications skyrockets, the traditional radio frequency spectrum utilized by Wi-Fi and cellular networks is becoming increasingly congested and prone to heavy interference. Li-Fi, a highly advanced subset of visible light communication, completely bypasses the crowded radio frequency spectrum by utilizing the existing LED illumination infrastructure to transmit vast volumes of data. Because solid-state LEDs can be switched on and off at extreme microscopic frequencies that are utterly imperceptible to the human eye, they can be utilized to generate highly complex binary codes. In a Li-Fi network, a specialized microchip modulates the high-speed flickering of an overhead LED lamp to encode massive streams of data. A sensitive photodetector on a mobile device, laptop, or industrial sensor receives these high-frequency light signals and instantly converts them back into electronic data. The advantages of this technology are profound. Li-Fi systems have been demonstrated in laboratory environments transmitting data at staggering speeds exceeding hundreds of gigabits per second, far outpacing conventional Wi-Fi. Furthermore, because visible light cannot penetrate solid walls, Li-Fi offers an unprecedented level of inherent physical network security. The data stream is physically contained within the specific room being illuminated, making it highly attractive for secure military, corporate, and hospital environments. Additionally, Li-Fi functions perfectly in highly sensitive areas where traditional radio frequency emissions are strictly prohibited due to severe electromagnetic interference, such as inside aircraft cabins or in close proximity to sensitive medical imaging equipment. As the integration of microchips into LED drivers becomes standard practice, the billions of light bulbs currently illuminating the planet possess the dormant capability to serve as a massive, ultra-high-speed, incredibly secure global data network. Next-generation display technologies, organic and microscale innovations. While the integration of gallium nitride LEDs absolutely revolutionized general illumination, automotive design, and horticulture, it also completely and irrevocably rewrote the architectural rules of digital displays. Standard liquid crystal displays, which dominated the consumer electronics market for over a decade, do not actually produce their own light. Instead, they act as highly complex, electrically actuated color filters that mechanically block or pass light generated by a massive, permanently illuminated LED backlight unit behind the screen. This traditional transmissive architecture suffers from several inherent, deeply fundamental physical flaws. Firstly, it is notoriously power inefficient, as the backlight must remain constantly illuminated even when displaying dark scenes. Secondly, and most critically for visual fidelity, because liquid crystals cannot physically block 100% of the intense backlight, standard LCD panels are mathematically incapable of rendering pure, absolute black. This light leakage results in washed-out contrasts, grayish-dark scenes, and a distinct lack of visual depth. The relentless quest for the perfect display necessitated a massive industrial shift away from transmissive backlighting and toward true emissive technologies, where each individual microscopic pixel generates its own independent light. This intense pursuit has culminated in the rapid evolution, massive commercial deployment, and fierce ongoing technological rivalry between two distinctly different yet equally revolutionary emissive technologies: organic light-emitting diodes, OLEDs, and micro-LEDs. The successful commercialization of organic light-emitting diodes fundamentally redefined the premium smartphone, wearable, and high-end television markets over the past decade. Unlike the rigid, highly stable inorganic crystalline structures of standard gallium nitride LEDs, OLEDs operate through the process of electroluminescence utilizing highly complex carbon-based organic compounds. Structurally, an OLED consists of incredibly thin films of these organic molecules sandwiched tightly between an anode and a cathode. When an electric current is applied across the structure, negatively charged electrons and positively charged holes are injected directly into the central emissive layer. As these opposing charge carriers inevitably recombine, they excite the organic molecules, causing them to relax and violently emit photons. The primary aesthetic and functional triumph of OLED technology is its unparalleled capacity for absolute pixel-level illumination control. Because every single microscopic subpixel in an OLED display serves as its own independent light source, it can be completely deactivated and starved of electricity when instructed to display dark content. This total, instantaneous cessation of light emission results in absolute perfect blacks and an infinitely high contrast ratio, providing a stunning depth of image quality, vibrant color pop, and perfect viewing angles that transmissive LCDs simply cannot achieve. Furthermore, the complete elimination of the bulky, rigid LED backlight unit and the complex liquid crystal matrix dramatically reduces the physical footprint and weight of the display. OLED panels can be manufactured to be mere fractions of a millimeter thick. Crucially, because the active organic compounds can be deposited directly onto highly flexible polymer or polyamide substrates rather than rigid, fragile glass, the technology has enabled an entirely new, paradigm-shifting era of industrial design. This flexibility has directly birthed visually striking curved screens, incredibly novel rollable televisions that disappear into their base, and the rapidly expanding market of fully foldable smartphone form factors that seamlessly bridge the gap between phone and tablet. Despite these massive, paradigm-shifting visual and physical advantages, OLED technology is heavily burdened by several severe intrinsic limitations stemming directly from its fragile organic chemistry. The organic emissive materials, particularly the specific compounds required to generate high-energy blue light, are highly susceptible to rapid degradation over time and exhibit acute, catastrophic sensitivity to ambient heat, oxygen, and moisture. Because the blue organic compounds degrade significantly faster than their red and green counterparts, the display inevitably suffers from uneven aging. Most notoriously, if static, high-contrast images, such as television network logos, video game heads-up displays, or smartphone status bars, are displayed for prolonged, continuous periods at high luminance, the heavily utilized organic pixels permanently lose their emissive capacity. This results in the dreaded, irreversible phenomenon known as burn-in, or permanent image retention, where a ghost of the static image remains permanently seared into the screen. To aggressively mitigate these severe degradation risks, panel manufacturers have historically relied on heavy-handed algorithmic interventions, most notably auto brightness limiter software. ABL drastically restricts the overall full-screen brightness of the display to prevent the organic compounds from overheating, which makes early and even modern standard OLEDs notoriously difficult to view in brightly lit rooms or direct sunlight. In a desperate, highly competitive bid to overcome these inherent brightness limitations while simultaneously preserving panel longevity, display engineers have recently developed incredibly complex structural variations of the technology, leading to a fierce market war between white OLED or WOLED and quantum dot OLED or QD OLED architectures. In white OLED displays, originally pioneered by LG Display, multiple organic layers emitting different colors are stacked vertically to emit a continuous, high-intensity spectrum of pure white light. This white light is then passed through a traditional passive RGB color filter to create the individual red, green, and blue subpixels. While this specific approach significantly improves manufacturing yields and overall panel stability, the passive color filters inherently block a massive, significant portion of the generated light. As a result, white OLEDs struggle to maintain high color volume, the measure of color saturation at high brightness levels. At peak luminance, white OLEDs must rely heavily on an unfiltered, pure white subpixel to boost brightness, which severely washes out the vibrancy of the colors. Furthermore, the unique subpixel layouts often required by white OLED technology can lead to noticeable text fringing and reduced clarity when used as a computer monitor. Conversely, the quantum dot OLED architecture, pioneered by Samsung Display, completely eliminates the need for light-robbing color filters. Instead, it utilizes a highly efficient uniform matrix of purely blue-emitting organic layers. This intense blue light is used to directly stimulate a front layer printed with incredibly advanced inorganic semiconductor nanocrystals, known as quantum dots. Because quantum dots possess near-perfect 100% energy conversion efficiency, they absorb the incoming blue photons and instantaneously, brilliantly re-emit them as incredibly pure, highly saturated red and green light. Because no light is blocked or wasted by filters, QD OLEDs are capable of achieving massively superior color volume, significantly higher peak luminance, and wider viewing angles compared to standard white OLEDs. However, QD OLED panels lack a traditional polarizer, which can cause their perfect black levels to appear slightly raised or purplish when viewed in brightly lit rooms with significant ambient light. To push organic technology to its absolute theoretical physical limits, the very latest iterations of ultra-premium mobile, IT, and automotive displays have introduced highly advanced tandem OLED architectures. By vertically stacking two distinct, complete organic emissive layers in series, separated by a microscopic charge generation layer, engineers have created a massive breakthrough in performance. This dual-layer architecture allows the system to be driven in two ways. Engineers can either drive the same amount of current through the system to effectively double the peak full-screen brightness, drastically improving high dynamic range performance, or, more crucially, they can run the panel at half the electrical load to achieve standard brightness. Driving the panel at half power reduces the thermal stress on the organic compounds so drastically that it extends the overall lifespan of the display by up to 4 times, effectively eliminating burn-in concerns and finally making OLED technology viable for long-term use in laptops, tablets, and automotive dashboards. As organic OLED technology rapidly approaches its absolute theoretical ceilings in terms of peak brightness and long-term durability, the global display industry is heavily pivoting its massive R&D budgets towards what is widely considered the ultimate final endpoint of display evolution, micro-LEDs. This revolutionary technology seeks to perfectly marry the absolute perfect black levels, infinite contrast, and microscopic pixel-level control of OLEDs with the extreme, blinding brightness, rock-solid durability, and infinite longevity of traditional inorganic solid-state LEDs. Structurally and conceptually, a micro-LED display is identical to the massive ultra-bright LED billboards seen in sports stadiums or Times Square, but miniaturized to an incredibly microscopic, almost unfathomable scale. Unlike OLEDs, which rely entirely on degradable, sensitive carbon films, micro-LEDs utilize the exact same highly stable, robust, inorganic crystalline semiconductors pioneered by Akashi, Amano, and Nakamura, specifically gallium nitride for blue and green, and aluminum gallium indium phosphide for red. However, these traditional chips are aggressively, meticulously shrunk down to dimensions often smaller than a single strand of human hair. Each individual subpixel on a micro-LED screen is an actual, physical, microscopic light-emitting diode chip. Because they are constructed entirely from robust, highly stable inorganic crystals, micro-LEDs are completely 100% immune to the chemical degradation, oxygen sensitivity, moisture damage, and permanent burn-in that constantly plague organic displays. They possess extraordinary thermal stability and can be driven with significantly higher electrical currents without suffering catastrophic failure or noticeable lifespan reduction. As a result, micro-LED panels are physically capable of achieving peak luminance levels measuring in the millions of nits, orders of magnitude brighter than the absolute most advanced OLED panels in existence, all while operating with significantly higher electrical efficiency and drastically lower power consumption. Furthermore, because the physical microLED chips are so incredibly microscopically small, they occupy only a tiny, minuscule fraction of the total physical pixel area on the screen. This incredible size reduction provides a massive architectural advantage. It allows engineers to coat the vast, empty space between the microscopic chips with highly specialized, incredibly light-absorbent black matrix materials. This structural advantage drastically reduces ambient light reflection across the face of the panel, allowing micro-LEDs to maintain incredibly high ambient contrast ratios in bright environments without ever having to rely on the light-robbing, efficiency-killing circular polarizers that are absolutely mandatory for maintaining contrast in OLED displays. The widespread commercialization of micro-LED technology, however, is currently stymied by a monumental, deeply complex manufacturing bottleneck known throughout the industry as the mass transfer problem. Fabricating a standard 4K resolution television display requires the precise placement of approximately 25 million individual microscopic red, green, and blue subpixels. In traditional LED manufacturing, chips are grown on sapphire wafers, sliced apart and individually packaged. However, for a micro-LED display, millions of these microscopic, incredibly fragile chips must be carefully detached from their epitaxial growth wafers and physically transferred to a massive thin-film transistor, or TFT, or CMOS backplane. This transfer must be executed with sub-micron absolute precision, ensuring perfect electrical contact without damaging the chips or the receiving substrate. To achieve any semblance of commercial viability, this transfer process must occur at blistering, unfathomable speeds, with a mass production yield rate exceeding 99.9999%. To put this in perspective, even a seemingly miraculous success rate of 99.9% would result in 25,000 dead, defective pixels on the final 4K display, rendering the product completely unsellable. Along with mass transfer, developing highly automated systems capable of rapidly inspecting millions of microscopic chips and physically repairing or replacing the inevitable defects remains a critical, massively expensive hurdle. To solve this physics and engineering nightmare, global technology giants and specialized startups are aggressively pioneering highly complex, science fiction-esque mass transfer methodologies. One prominent approach utilizes highly advanced elastomeric pick-and-place techniques. These systems rely on custom-engineered micro-patterned viscoelastic stamps, often made of specialized polymers like PDMS, that are capable of adhering to and lifting tens of thousands of microscopic chips simultaneously from the donor wafer by precisely manipulating microscopic van der Waals adhesion forces. The stamp then moves the array of chips over to the display backplane, where the adhesion strength is chemically or mechanically reversed to perfectly deposit the chips onto their designated electrical receptors. Alternatively, the industry is heavily investing in laser-assisted transfer, or LLO technologies. This photon-based technique utilizes incredibly precise high-power ultraviolet excimer lasers. The laser beam is directed through the transparent sapphire growth wafer from behind. The intense pulse of UV light instantly vaporizes a microscopic, highly specific sacrificial buffer layer, often gallium nitride, that was intentionally grown between the micro-LED and the sapphire substrate. This rapid vaporization creates a highly localized microscopic kinetic shock wave that literally, physically blasts the microscopic chip off the wafer, pushing it perfectly across a tiny gap and directly onto the adhesive-coated receiver panel. Even more exotic, highly experimental transfer methods include fluidic self-assembly. In this staggering process, Millions of individual micro-LED chips are suspended in a specialized liquid medium. This fluid is then swept continuously across the surface of the display backplane. The process utilizes carefully calculated physics, gravity, fluid dynamics, capillary forces, and unique, highly specific geometric interlocking shapes etched into both the chips and the substrate to force the chips to autonomously drop into their precise designated electrical vias like puzzle pieces falling into place. While currently restricted to ultra-premium, astoundingly expensive large-scale televisions and commercial video walls due to these astronomical manufacturing challenges and costs, the ultimate, most critical application for micro-LED technology lies in the rapidly expanding, highly strategic sector of wearable technology, specifically augmented reality, or AR, and virtual reality smart glasses. The fundamental optical physics of true augmented reality require highly complex digital images to be projected through transparent, highly reflective optical waveguide lenses so that the holograms can be seamlessly, perfectly overlaid onto the user's view of the real world. These waveguide optical systems are notoriously inherently highly inefficient, often losing or scattering over 90% of the light injected into them before it ever reaches the user's eye. If an AR headset attempts to utilize an OLED microdisplay as its light engine, the organic limitations on peak brightness mean the digital holograms will be completely, instantly invisible the moment the user walks outdoors into bright ambient sunlight. MicroLEDs definitively, fundamentally solve this critical optical failure by packing millions of microscopic, ultra-high-intensity, inorganic gallium nitride chips onto a monolithic silicon CMOS backplane the size of a postage stamp. Engineers can generate the millions of nits of raw, unadulterated optical power absolutely necessary to force the image through the highly inefficient waveguide lenses. The resulting holograms remain vibrantly, distinctly visible even in direct, high-noon sunlight. Furthermore, because microLEDs are self-emissive, do not require bulky backlights, and are vastly more electrically efficient than organic OLEDs, they drastically reduce the thermal heat output and battery consumption of the headset. This allows hardware designers to shrink the required battery size and eliminate heavy thermal heat sinks, paving the way for AR smart glasses that are as lightweight, sleek, and unobtrusive as standard prescription eyewear, fundamentally unlocking the next monumental era of spatial computing and human-machine interaction.